No, it's really my pleasure. Thank you all for coming. It's my great pleasure to actually introduce our speaker tonight. I am honored to be able to call Rob Toonen, not just a colleague, but a dear friend, actually, for about 20 years now. He's also a fellow martial arts practitioner, and so we share that. And I am just going to embarrass him for a few minutes before I introduce. I actually, if I gave you all of his accolades and accomplishments, he wouldn't have any time for his talk. So this is a very truncated list. But he received his master's in Joseph Pollack's lab at University of North Carolina, Wilmington, and moved on to UC Davis for a PhD with Richard Grossberg in population biology. He is actually, as you can see up here, he's tenured research faculty. He's the Ruth Gates Endowed Chair of Coral Reef Studies at HIMB and the director of the Mānoa Marine Biology Graduate Program. Both of those are also very busy positions. He's also the chair of the Reserve Advisory Board for the Hawaiʻi National Estuarine Research Reserve and served as their interim reserve manager for 4 years. His research spans a variety of disciplines from larval biology to ecology, population genetics, and in marine invertebrates. And what he's really famous for is his work in marine ornamental aquaculture and aquarium science. He's always told me that he gets more hits on those publications than any other science publications. He's a fellow of the International Coral Reef Society and is recognized as among the world's leading researchers in coral reef ecosystems. He is the only faculty member at the University of Hawaii who holds the distinction of receiving the Board of Regents Awards for Excellence in Teaching, Excellence in Research, and the Willard Wilson Award for Distinguished Service. All three, the triple threat. His recent research focuses on how coral reef ecosystems now respond to human impacts. And so as you can see up there, he's going to talk to us about the future of coral reefs in Hawaii and technology to reverse coral reef loss. So please help me welcome Rob to this lecture series.
Thank you very much.
You're very welcome, and of course you know I'm not going to hug you because I have a cold.
Yes. Thank you. Grab this. Well, I wanted to start off by thanking everyone for coming this evening and just telling you a little bit that I'm originally from northern Canada. The closest ocean to where I grew up was the Arctic, and the way that I got excited about coral reefs was reading the work of Bruce Carlson and Charles Delbeek, who set up these amazing coral reef displays in the Waikiki Aquarium. I had every one of the books. I started in high school managing a pet shop and worked my way through college as a coral reef aquarium expert. And so it has been a lifelong inspiration to me, and it is an honor to be here this evening and to help restart the Tim Gard Distinguished Lecture Series. So thank you very much. Today I would like to talk to you about coral reefs. They are incredibly important ecosystems. They have a very small footprint on the planet, but have over 30% of the species of marine species. They feed almost 1 billion people on the planet. They generate about $1 billion of economy in the US alone. And if we sum up all of the ecosystem services that coral reefs provide for the planet, it's estimated that that is about $9 trillion a year. And yet we are losing them everywhere. Everywhere that people are talking about coral reefs, we see this trend of coral decline from a whole suite of local and global threats. And this is something that scientists have been trying to bring attention to. How many of you have seen Chasing Coral, this documentary? So a fair number. Does a fabulous job of explaining what the challenges are and bringing a lot of attention to mass coral bleaching on the planet. And just in case people aren't familiar, I need to explain corals are a blend of an animal and a plant. So if we look at a coral skeleton here, on the outside of that coral skeleton, there is tissue. This is animal tissue that is full of these small brown dots. We call them zooxanthellae, which is a really fancy word for brown dot. They're actually dinoflagellates, and those dinoflagellates are photosynthesizing and producing food for the coral. If the water temperature increases, that healthy coral starts to lose all of those zooxanthellae from the tissue. And so as those zooxanthellae are kicked out, what we start to do is see the reflection of the white coral skeleton underneath, and we refer to that as bleaching because they become white. And as soon as that happens, the coral's not getting any food. And so the timer starts. If we stop feeding you or me, we have a timeline before we expire because we eventually run out of energy. And if that happens, the coral dies and it is grown over entirely by algae. But if that coral that is bleached is gotten back under good conditions, this process can reverse. It can recover its symbionts, it can start to feed again, and it can go back to this healthy state. And so this is something that a lot of the news media seems to forget, is that coral bleaching does not automatically mean death. It means that corals are stressed and it needs some opportunity to recover before it goes to that point. And yet we see tons of these types of news articles out there. More than 90% of the world's corals are lost. I don't know, we'll come back to this later on. If people saw this was huge news right before Christmas, that coral reefs are the first ecosystem on the planet that has reached their global tipping point. And where do those predictions come from? Well, if we look at the predictions of future climate, we have a lot of variability depending on which model we look at and how bad. If we just stop burning all fuel right now, we have an orange line, and depending on how badly we fail at that, the temperature goes up. And if we take a look at what's happened to global temperatures from the 1800s to 2025, we're somewhere around the purple line here. And if we take a look at, based on those models, where do we get to the point where corals will bleach every single year? That's somewhere in this 2050 range. So if we get to the point that we're about a 1.5 degrees warmer oceans, then that prediction is that we will get to the point where corals bleach every year, so they will cease to exist on Earth. And this is where I have to explain to you about the amazing counterexample of Kaneohe Bay. So Kaneohe Bay has a just beautiful area. It's known as the Coral Gardens. Fabulous historical reefs that we used to have a glass-bottom boat that would do tours there. People talk about it all the time. And then someone had the bright idea to build a sewage plant and dump it into the southern part of the bay. And those were some dark years for Kaneohe Bay. We lost most of the coral cover. We got down to an average between 7 and 10% coral cover across the bay as most of that coral died off. But the community organized, there was a lot of pressure. People managed to get that sewage outfall moved offshore. And today, the bay has come back to some of the highest coral cover in the Hawaiian Islands. So this is a fabulous success story of changing local stressors has resulted in the coral reef recovering. But, oops, 2 slides. So this is Moku'oloi, where the Hawaii Institute of Marine Biology is located. This is where I have the privilege of working. And we frequently refer to this as an ocean of the future because the bay is formed by the fabulous views here of the Ko'olaus. This was a volcanic caldera. There was the Nu'uanu slide about 1 million years ago where the side of the volcano slid off. And these incredible steep slopes are what's left of one side of it, and the shallow, huge bay is the other side of it. So this bay has been in existence for a long time, and it has a barrier reef along the outside edge that limits exchange with the open ocean. And so if you think about what happens when you have a large shallow bay in the tropical sun with limited exchange, well, what happens? It warms up. And if it's full of life that is breathing and producing CO2, it also tends to reduce the temperature, reduce the pH of that because we're producing CO2. So here's an example plot looking at the offshore temperatures are here in blue, and based on a couple of different instruments, whether it's in red or mustard here, these are the temperatures in Kaneohe Bay, and you will see that they are both much higher and much lower than the offshore temperatures. Kaneohe Bay already averages about 1.5 degrees warmer than a lot of the coastal oceans in Hawaii. And so in 2025, just before Christmas, the Global Tipping Points Consortium came out with a report saying that coral reefs are the first ecosystem on the planet that has reached the tipping point and crossed it, which means there is nothing left we can do. They are doomed. And aside from me fundamentally disagreeing with that statement, that is a terrible message to send out to people. So let me explain to you where that statement comes from and why I think it's fundamentally wrong. So this report is based on this rationale that assumes that corals cannot adapt to temperature, that it's just happening too fast or they're too slow growing, and that the loss of corals will happen as soon as they bleach on an annual basis. But Kaneohe Bay gives us a fabulous counterexample to that because the global tipping point that they predict is the conditions that are already happening every day in Kaneohe Bay. And up until we moved the sewage outfall, we had basically managed to get rid of corals in Kaneohe Bay, and yet under future ocean conditions, they came back gangbusters within 30 years and have some of the highest coral cover that we now have in the main Hawaiian Islands. And what's even more sort of interesting about that example is if we look at historical reconstructions of coral cover in Kaneohe Bay, the best guess estimate is that we had roughly the same human population, pre-contact Native Hawaiians, in Kaneohe Bay as we do today. So we have the same number of people living for about 800 years of sustainable harvest without decreasing the coral reef condition, and then it plummets here somewhere between 1930 and 1950. So what's going on there? Well, we decided that we were going to build the city of Kaneohe, make a sewage treatment plant and dump all of the sewage into the bay. We started to change the agricultural system, so there's all of this sedimentation and runoff, extensive dredging of the bay to build up the Mokapu Peninsula, and all of these things correlate with the loss of coral in this area. So I would argue that Kaneohe Bay gives us a nice model to understand what futures of coral reefs might look like and try to understand how can we make sure that our reefs don't disappear into the future. And so this is some work that was done by Chris Jury, who was a student in my lab at the time, who now works at the Waikiki Aquarium and is sitting in the back hiding. So if folks have questions about this, you can ask him. He did these amazing studies where he developed 40 of tanks looking at sort of current day conditions, tanks that were heated, tanks that were acidified with ocean acidification, and then future conditions where both heating and low pH happen simultaneously. And he stocked these things with sort of natural densities of what we would expect in terms of fishes and snails and such, and then ran this for a couple of years in these flow-through systems to ask the question, how do the coral reef communities respond to these different conditions? And what he found was there is no tipping point where corals just crashed. These tanks had mid to late century sort of conditions, annual bleaching, very severe conditions, and yet the corals still grew gangbusters, and in many of the tanks were almost half full. But what's really interesting out of this experiment is that you get a totally different group of species that start to dominate under these different conditions. So if we look at the controlled conditions, and this is work that Chris and Molly collaborated on trying to look at what do we have. And so we've got, in addition to just our corals, we've got a bunch of worms and sponges and snails and brittle stars that are living in these tanks. And if we look at just the top 10, they went through and they basically figured out everything that was in every tank, the bacteria to the corals to the algae, everything, and asked the question, what's there? So this gives us sort of a baseline to compare against. And if we look at the tanks where they decrease the pH, what we see are sponges and brittle stars and worms really take over. They dominate these systems. In the heated tanks, we see a different group of sponges that takes over, along with snails, and actually the corals did okay. And so we have these two different groups, different sets of organisms that are dominating. And the normal prediction is if acidity is bad and if heating is bad, then double whammy must be twice as bad, right? And instead what we find are there are other groups that take over under these conditions. And in particular, amphipods, which are little reef grazers, they eat algae, they did great because we had a bunch of algae. So it turns out that this crustose coralline algae, the pink hard stuff that you see when you go down to the beach, often see pink rock, this is actually a crustose coralline algae. And what a lot of people refer to this to as coral flypaper, because this is what coral larvae love to settle on. And many people have argued that this will be one of the first species that's lost under future ocean conditions, but they've only ever done them one at a time. And what Chris was able to show is that, in fact, they do really well when you have both conditions. And so in this case, two bads made it better, not worse. And if we look at the total groups of species, everything that's in the tanks, there's no significant difference in total biodiversity among any of these. And if you look at the comparison, acidity is out here, so on one side, heating is over here on the other, and the future ocean and control are almost perfectly overlapping. They're the two most similar of all of the treatments. And everybody typically does heat, control, acid, and says, these things are going to be bad, so when we combine them, it's going to be worse. The other thing people always say is there's no way that corals can adapt to climate change. It is happening too fast, and corals are too slow growing. And that's something that we actually have some real data for in Kaneohe Bay. Steve Coles here did his PhD, and he published in 1970, where he actually took corals from right off of Moku'oloi, and he asked the question, if I warm them up, how many days do they survive? How long does it take for them to bleach and die? And in 1970, when he did his PhD, everything was dead by 13 days, and there's no corals left in that experiment. In 2017, Keisha and Ku'ule came along and repeated the experiment, the exact same corals from the exact same place, and found that actually they're doing pretty well. And for a month out, they have almost no decline in those corals. They're surviving so much better, and they have between 3 and 5 times more temperature tolerance after, give or take, 50 years there. And if we take a look at how much the water temperature has changed since 1970, the actual water temperature in Kaneohe Bay has increased by about 1.13 degrees, but the bleaching tolerance of some of the corals in this experiment had gone up by as much as 2.8 degrees. So this claim that corals cannot adapt, and they cannot adapt quickly, is simply not supported by the data. And so when people talk about these global die-offs and that corals have passed a tipping point, if they assume that there's no possibility for adaptation, then the only prediction is that coral reefs cease to exist when some of them die. But if you allow for adaptation and reduce local stressors, perhaps that future starts to look better. And I really want to emphasize the reduced local stressors because when we look at Kaneohe Bay as an example, it's not temperature that's driving this decline. The temperature in the bay has been stable for literally now thousands of years. And it's these human activities that have correlated with this decline. And there's tons of research now coming out over and over where people show that reduction of local stressors has huge advantages to keeping corals from dying during these marine heat waves. We have a real need for coral reefs in terms of our economy, in terms of supporting people's lives, and yet we still keep having news like this where we are losing them. So what do we do about that? It's one thing to document the loss, but there's another option that we can actually try to be part of the solution. And part of this is just looking at the amount of money that we would spend for coastal protection if we didn't have our coral reefs. So if we take a look at the USGS and their expected annual benefits of corals for protecting the shoreline, there's two places under US jurisdiction that pop out as being above $1 billion a year, and Oahu is one of them. So if we didn't have coral reefs, it would take on the order of $1.8 billion of our taxpayer money to replace all of the damage that coastal erosion and storms were causing to our infrastructure, like our highways, our airports, our power plant that are all right next to the sea. And we see this in our news, right? Like, anyone who's driven up Ka'ava has seen this photo. We all saw on the news as the houses are starting to fall in. These things are happening right now. And, just looking at the values, all of these areas that have blue highlights around the island of Oahu, 1 kilometer of this shoreline would cost us $1 million a year to protect. So we can't afford to lose our reefs. This is part of a team. I'm one of the team leads for this project that is called Rapid Resilient Reefs for Coastal Defense. This is a project that includes biologists, oceanographers, ocean engineers, economists, trying to figure out how can we learn from nature, take the designs of a coral reef, and engineer something that will protect our shores and serve local communities. And so the project is basically, can we protect the shore? Can we take out waves, reduce wave energy by about 90%? You got to increase the natural coral recruitment without growing a whole bunch of algae on them, because anyone who's put anything in the ocean knows like a month later it's covered in algae. It's got to survive marine heat waves. It's got to increase biodiversity. Oh, and by the way, it can't cost more than just pouring concrete, which seemed like an impossible goal when we started off. But people have been working on this for a decade, and we've come up with some concept designs that we think can actually maybe meet those goals. So this is Zhenhua Huang, who's standing here in a flume. This is a 1/6 model of the design to test how well it works. This is the full-scale version of that. So the structures, the large structure here is about the size of a Matson shipping container. And then the little back reef structures are only about 5 feet tall, 8 feet wide. They're still huge. But in terms of how they work, if we look at the 1/6 model, this would be the equivalent of an 8-foot wave coming in, and it doesn't make it to shore. So this is able to take out an 8-foot wave on this design. By having an open porous design, it allows the wave to pass through it. It creates internal turbulence, so the wave basically beats itself up as it goes through, takes out the energy gradually so it doesn't cause scour and move sand around, and actually manages to reduce that wave energy. But we also want there to be corals on there. And so this is work where we've been trying to figure out all of these individual habitat structure models, modules that we can try to get organisms to grow on a concrete reef. So one way to do that is you take coral fragments and you break them up, and it's just like plugging a lawn. You glue them around the structure, they start to grow together, they fuse, and they cover up that structure. We can take individual pieces of coral and make them on plugs. And this is a design that is actually to specifically promote individual coral settlement. So those settlement domes that have been designed by Josh Maiden's lab, you can see all of the little green dots here are coral larvae that are settling on these structures. And what he finds is this particular spiral dome design outperforms all the others and can get up to 80 times more settlement and up to 50 times more survivorship than an actual reef can. So these things are actually attracting larvae and pulling them in. Daniel's been working on these biodegradable anti-algal coatings. Like I said, if you put anything in the ocean, within a month or two, it totally is covered with sponge algae. It looks like this. And he has these little slippery coatings that every wave that comes by cleans the surface for us. And after 2 months, that thing is still totally clear. The algae cannot seem to get a grip on it, and every wave cleans it off. But corals don't seem to care, and they go right through it. So we can actually use this to keep the surface area around the corals clean, allow them to get a head start before they have to start competing with the algae. The way a lot of, particularly reef fish, but also corals, it turns out, find a good place to settle is that they are using sound. And it turns out that if you have the sound of breaking waves and the sound of a lot of fishes eating, that might be a good place for you to land and to settle in and start your life. So while these fish are out as little tiny plankton, they're floating around in the open ocean, they're trying to decide where are they going to land and start their life. They are searching for cues, and one of those important cues is a lot of other fish feeding. So Aaron went out, recorded a whole bunch of fish feeding in an area, put it up, set it up in an area where there's absolutely no coral reef and no fishes, and he played this sound, and he gets from the speaker down along a gradient, he gets huge increase in settlement where they're playing the happy reef sounds, and then he turned it around the other way, and all of the fish that were settling close to the speaker stopped doing that and went to the other side. So it's not the habitat, it really is the sound. And we could also work on outplanting things like native urchins, so working with the Division of Aquatic Resources, who's breeding these things, putting them out to try to control algae, working with native Hawaiian communities to incorporate traditional practices like umukai, where they use them to recruit juvenile fishes and increase food security as well as diversity in these systems. So adding all of that habitat is with the goal of can we actually create a diverse coral reef? And so what we've done is we've been testing every type of material People talk all the time about concrete is not good for the ocean and it's not good for corals. We got every material we could possibly get our hands on, including many very expensive eco-friendly things, tried them side by side, and it turns out Quikrete from Home Depot did just the same as the most expensive stuff we could find. So we started working with, well, okay, the material doesn't matter. What is the design and what is the cost? How do we design things that have lots of pukas for lots of different life? We tried a whole bunch of different strategies for, does it help if the fragments, when you're plugging the lawn, do they have to all be the same size or can they just be different sizes? And it turns out that dropping a coral and just letting it break costs the least and works just as well as spending all that time and money making every fragment exactly the same because it's labor that turns out to be the biggest investment in a lot of these projects. And then really thinking about how do coral reefs assemble, how many different species do we need, what are different corals doing. People often talk about corals and then stop there. It's like corals. Well, that's kind of like saying vertebrates. I'm a vertebrate, and so is a goldfish. I don't think you would come and listen to a talk by a goldfish. We do different things, we have different skills, we do have all sorts of different activities and specialties that these organisms do on the reef, and we need to incorporate them if we're actually talking about making a reef work. And then this is the Maiden Lab's spiral domes again, but you notice there's all these holes in there. And that's because the Coral Resilience Lab with Ford Drury has been working on, when you go out in the wild and you see during a bleaching event, there's one coral that turns stark white and the coral right beside it stayed brown. And people always have said, like, why, what's going on? Like, how is it that one coral bleached and the coral beside it didn't? Well, it's like us. One person can get sick, another person may actually not get sick, even in the same house under the same conditions. So there's a lot of individual variation out there. And what Ford's lab has been doing is working on, if we go out and find those individuals that went through a natural stress event, and we collect the gametes from those, we can actually breed individuals, just like we might want to take a breed of dogs. If you take the biggest ones, and you breed them up, you eventually get a Great Dane. If you take the smallest ones and breed them down, you get a Chihuahua. Well, we might want to say, let's take a look at all of the ones that are most resilient to future temperatures, put them out, take all of those things, raise up all of these tiny little larvae. So this is 0.5 millimeter. These things are very, very tiny. They can be raised up in the lab, they can be settled out on these pins, grown up, and then they can be stuck into those plugs. So we can increase the temperature tolerance of the corals by helping nature to find the most temperature resilient individuals. And even when things go wrong, maybe there's something we can do about it. And so what we've been doing is testing different technologies like this, where you can just simply take an off-grid swimming pool pump and a solar panel, hook it up to some foam jets, and spray foam on the water. Well, it turns out this can reduce the light by more than half, and that is enough to protect the corals from bleaching in areas where they are actually getting too hot. The other thing you could do is maybe feed them. So people have seen maybe the manta rays on the Big Island where they put out lights. They attract all of the plankton to the lights. We can do the same thing. And this works really well, particularly for baby corals that have just settled. And so by basically having this little timed underwater flashlight that turns on for an hour each night, it brings in a whole bunch of zooplankton, it feeds up the coral, gets them fat and happy, and helps them to survive some of these rough times. And all of this has been done so far in the lab, but we are now finally at the point where we are headed into the final permits to try this out in the field. So the plan is at Keleloa, off Campbell Industrial Park, All of these things are assembled, they are now built, they are waiting the final permits from DAR to be installed and to be tested in the field and to see, can we actually build a coral reef in a place that doesn't have one? And does this take out wave energy and protect our shoreline? Can we increase food security and shoreline protection at the same time? And if not, how do we fail, why do we fail, and how do we improve it? So that is the goal of the project and where we're at right now. And this is the impetus, I guess, for the newest aquarium exhibit that will be starting up. So I encourage all of you. Josh Maiden has been working on this. This is what AI came up for me for the concept design of what the tank might look like. But Josh has been working on these designs, trying to 3D print out structures and to communicate this technology to the public, and this will be one of the new exhibits later this end of summer?
Yeah, a few months.
Few months. So I encourage everyone to go and see that. And with that, I will stop and take any questions that anyone has. Tony.
There's been a lot of bleaching on the barrier reef in Australia. There's a lot of communication about that. Their local stresses, those reefs are between 18 and 50 miles offshore.
Yep.
How devastating are the local conditions, the local stresses, as opposed to just hot water?
So there are several layers to your question. So one, I would start off by saying, yes, the Great Barrier Reef has had a huge amount of coral bleaching. They have also reported record numbers of recruits, the highest that they have ever seen, over and over again after every one of those bleaching events. So it comes back to bleaching does not equal death or loss of reefs. So when people talk about bleaching, we have to ask what was the consequence of the bleaching and not just say it bleached, therefore it must be bad. But the flip side of that is people often say, oh, it's far away, it's like miles away. If we actually calculate the amount of sewage that the city of Sydney puts into a river and calculate the spread over 30 miles, I would argue that every ounce of Great Barrier Reef has been through a toilet. So those stressors do add up over time, and people have to remember that the way we are treating our sewage, the runoff of sediments and all of those things on land is having effects in the ocean. And that is something that I find a lot of people sort of talk about. Climate change is something we can't do anything about. And I worry that gives us a scapegoat to not do anything. And I would argue local stressors are something we can all do something about, and that's what's going to have the biggest benefit for coral reefs. Yeah.
Just curious how important the magnitude of daily fluctuation in Kaneohe Bay is compared to open coastal environment where the increase in temperature might be more unidirectional.
So this is actually a fabulous segue. So the late Dr. Ruth Gates, she and I started our jobs at the same time. She was a physiologist, and she always argued that that magnitude, that was exercise. And the corals in Kaneohe Bay were marathon runners. That's why they could survive. And I'm an evolutionary biologist, and I would say, it's the genetics and it's evolution, and they're adapting, and that's why they can survive. And we spent years having lunch together arguing about it and doing research to prove each other wrong. And of course, it's biology. We were both right. Those things all happen simultaneously, and organisms are responding to their environment all the time. There's physiological adaptations to change, like they're making changes in their lifetime to be better at those highly variable conditions. And evolution is selecting for the ones that do the best over time. And there's no single answer. Biology does everything it can to survive, and they both matter. Yeah.
First of all, wonderful talk. Thank you very much. So you've offered Kaneohe Bay as kind of an example of the future and that things may not be so bad. But in Kaneohe Bay, as you pointed out, the temperatures are 24 to 26 degrees. In the tropics, where most of the corals are, it's more like 30 degrees.
Yeah.
How do you know that what you're seeing and changing from, an additional degree at 26 degrees is going to apply for corals that are normally living in 30 degrees that maybe have to go to 32 degrees?
Yeah, so can everyone hear the questions or should I repeat them? There, all right, okay. So I find this is a very common point that people make to dismiss Hawaii as not being important to coral reef biology everywhere. But in fact, the way that we predict coral bleaching has nothing to do with the absolute temperatures. It is the temperature above the mean monthly max of where you live, which is when corals bleach. Corals across the entire planet, irrespective of where they live, in the Red Sea or in Hawaii, all bleach at about a month, 4-degree heating weeks above their mean monthly max. So corals clearly have adapted to the average temperature at which they're in and are trying to maximize how close they can get to that tipping point to continue their growth at high temperature before they fall off the edge. And corals are doing that everywhere on the planet. They have done it because if we look back in the glacial times, 18,000 years ago, there wasn't a coral reef on the planet where it is now. Sea level was 130 meters lower, and every coral reef on Earth has come in the last post-glacial time. So during that time, they've all figured out exactly the temperature 1 degree below where they average. And I would argue that it doesn't matter what the absolute temperatures are. It matters what you are in your environment, and that corals are all doing the same thing across the entire planet.
Thank you for the talk. You failed to mention whether or not your prototype reefs are cheaper than concrete.
So they're certainly not, because they are research and they included a lot of people's salaries. But the goal for the prototype reef is that we are, if we consider the scaling for what the state of Hawaii has paid for Hilo Harbor or any of the local, the large-scale breakwaters that they have made in the past decade, we're in the same ballpark as them for the actual construction and deployment of this reef. So the real question, yeah, it's in the same ballpark. The real question is, does it perform well enough to justify the slightly higher cost? But it also shouldn't, hopefully, as we scale up, it should actually, you see the scale of the economy of scale as people start to produce these. So if it works, I think we will be pretty close to the actual cost of what the Army Corps of Engineers is currently doing with breakwaters. Yeah.
So the thought about these artificial reefs is to put them in places like the highway up by Haulula.
That would be the goal, is to work with, and I would say, first of all, this is not a silver bullet. It's not the solution for everywhere. But for communities that want this, want to have a solution where building up the coral reef will give them time to protect their roads or their highways or their homes, this is something that we hope will be able to solve that problem. And so that is the goal. But one of the common questions I get when I try to talk to communities about this is like, can we still surf there? I was like, actually no, because if we take out the wave energy, that's what you are riding. And so communities need to be able to decide, if you are saying, well, okay, we're going to take out all the wave energy, then which do you want? Do you want to surf that break, or do you want a highway so you can drive to work? That's an answer that people are going to have to struggle with if they're starting to look at this. And you could design it to make a surf break as well. It's a totally different design. But these engineering solutions are tailored to specific conditions that communities want.
there's also a risk, I assume you thought about it, of kind of empowering people that, oh, this isn't actually as bad as it sounds. I mean, I know you want to be honest and everything, but to give people an excuse that, oh, we can keep kicking this down the road, and they've been saying this for years, the scientists keep lying to us, that kind of stuff. Kind of the other end of the spectrum. If that makes sense.
Yeah, I think it's a fair question. And so I hear this a lot from scientists who say giving people any hope that this might not be as bad as we thought might discourage action. I would argue the opposite, because what I find is when you tell people there is no hope and we've crossed a tipping point and it doesn't matter what we do, we're going to lose coral reefs, then why would anyone care about spending money on it? This is something that we are facing right now. Coral reef decline is happening before our eyes. And we have things that we can do, like changing how we're disposing of our sewage, or the amount of sediments that are going into our nearshore waters, or how many herbivores we are harvesting off of our reef. Those are things that people can do to increase the amount of time that we have. And if we don't do anything, then we're going to continue with the trend that we've got.
Yeah.
And,
Agreed.
Yeah.
And is there a call to action? Like, is there something people here could do or tell their friends about? Like, you guys need money or volunteers or?
I wish I had thought about that in advance. That is a fabulous question that I will have to get back to you on.
Sure. And final point, I would definitely see a lecture by a goldfish. Thank you.
Yes.
So for the anti-algae coating on the plug, is it going to be applied on those bigger 3D structure as well? And then if it does, do you think it's going to impact the local settlement rate if it's just like larger scale?
So the coating is pretty small scale, and what it's primarily being used for right now, on the structure at least, is that places where you glue down a piece of coral, if you just leave that there, it takes a while before it starts to grow out and actually establish beyond the piece that you've cut. It has to grow out onto the concrete. And if algae starts to grow there first, the coral's in direct competition with it, and the algae grows faster. And so the way that we're using it right now is, Daniel calls it a coral guard. He's basically using it sort of as a Band-Aid around the coral, giving it a chance to grow without any competition for the algae until it attaches through that structure. And so it's not going to be huge areas, it'll be patches where the corals are growing specifically. And the stuff lasts for 8 months or so, and then it just sort of breaks down and sloughs off, and that's enough time for the corals to get a pretty good head start. Yeah.
Well, thanks so much. I'm interested in what you said earlier about this sort of design for dissipating wave energy versus designing for what we would consider maybe a natural reef that we want to surf on,
Yep.
right, or something. So how much different are those? Because a natural reef does have porosity,
Yep.
it has the reef structure, it
Right.
has, so I'm just curious, like how far away are we from those two options of just both dissipating wave energy, but also
Yeah.
supporting recreation?
And there are certainly compromises that can be had in terms of how the wave energy is dissipated. But if you think about where we have big wave surf competitions, like the North Shore, we don't really have that much reef right there. So places where people are really focused on big wave surfing and that sort of thing, maybe that's not the place for this type of technology. Or maybe there are areas where you're actually encouraging a wave and you're designing it so that will be there. But then those waves are going to break on something. And if that is your coastal highway, then you have that consequence too. So there are things that still need to be figured out in terms of the policy. The technology can handle either of those solutions. You could also think of like wave energy generation or lots of different things that could be incorporated into the design. But first we have to prove that it actually works the way we think it does. Any other questions?
All right, well, if no other questions, will you help me thank Dr. Toonen for his...
Thank you.